guys, it's part 2 of exponential functions, and we actually want to now go graph and see what exponential functions look like, what common features they should have, and then we'll actually look at transforming those exponential functions using translations left and right, up and down, and your stretches and things like that. Okay, so just to be able to describe some movements. Let's look, okay, at first of all, b to the x. Okay, so that is an exponential function where b is greater than 1. Okay, so remember we could have b is greater than 0. We did not want it equal to 1. Okay, so we're breaking it up into 2 parts. We're going to look at it where b is bigger than 1 and then where b is between 0 and 1. So let's go look at what b greater than 1 gives us. And so we're going to go use Desmos to do that. Okay, and we're going to use our little slider. So we're going to put maybe b to the x. Okay, and here we can add slider. Now, see, this is why we didn't want to do b equals 1, because it's really boring. It's just a line at y equals 1. So let's see what happens when we get bigger than 1. Okay, so there's our shape. Let's move it to 2 a minute. This is what we did at the end of class last time. We talked about 2 to the x. Notice we had 0, 1 as a point. We had 1, 2. Okay, we had 2, 4. So those are all points we had put on our t-table. Okay, so here's our basic graph. It hugs the x-axis on the negative side, and then it goes up quickly. Okay, so what happens as we get even larger? It maintains that same shape, but it's getting closer and closer to that y-axis. It's getting steeper and steeper. Okay, so the shape stays the same, and that shouldn't surprise us because we have parent functions, right? And so all exponential graphs should look the same. So as we get larger and larger, it just gets steeper and steeper quickly. Okay, so this is what an exponential graph looks like. Okay, some points to notice. Let's go back to 2, maybe. Okay, is that you will always have a y-intercept. Okay, and it will be 1 unless we move up and down. Okay, if we move up and down or if we move left and right, that 0, 1 can change. Okay, so think about it a minute. Why is that point always going to be 0, 1? Well, it's because anything to the 0 power is 1. So unless we change it somehow with a transformation, we should always have a y-intercept of 1. Okay, something we should also have is at 1, right? If we plug in x for 1, or 1 for x, excuse me, we should always get our base. So in this case, we have 1, maybe, it doesn't want to show me. Okay, should be 1, 2, okay, because 2 to the first power is 2. Okay, so we should always have those common features. We should have a y-intercept here, and then 1 comma whatever your base is. So let's check that out. Let's go to 5. So do we still have a y-intercept of 1? Yes. Okay. And then at 1, 5, we also have a point. Okay. Then if we moved it to 10, notice we still have a y-intercept of 1. And no surprise, we should have a point at 110. Okay, so those are very important points, if you will, on an exponential function. Okay, so let's go ahead and describe that on our notes. So let's just do a quick sketch. Okay, doesn't have to be perfect or anything. And I'm going to have 1 here. But everything should have this basic picture. And let's go ahead and label these 2 points. This is always 1, comma b, because, can you give me the other one, please? Is there one more? Okay, thank you. So b, right? So we have our base here, b to the first power is always going to be b. So that's why we have that. Okay? And then this point will always be 0, 1. Okay? Again, unless we have to move it due to a transformation. Okay? So those are very important points. Let's go ahead and just write those over here then. So we get 1b and 0, 1 are 2 points we would always expect to see on a basic exponential function. Okay. Now, what would you tell me the domain of an exponential function is? Okay. Well, the domain is the x values. So x values can be anything here. We have all the way from negative infinity to positive infinity. Okay. So no restricted domain. Okay. About range. Okay. Is there anything that y cannot be? Okay. Well, we never go below that y-axis, or excuse me, the x-axis. So that means that 0 is a limit. Okay, and then we go as high as we want. Okay, now does this ever touch 0? Okay. From the graph, we can't really tell, but if we think about this, is there any way to take a power and get 0? And the answer is no, so that should be a parenthesis. Okay, so it's always positive numbers. This is a really important part when we get into logarithms because they're inverses, which means the domain and ranges switch. And so that means we can only take logarithms of positive numbers. Okay, so we'll talk about that next week, but that is a consequence of being an inverse. So, do we have any asymptotes? I would definitely say yes, we have a horizontal asymptote. Okay. And specifically, it is the negative x-axis. Okay. All right, so that's just an important feature here. So, kind of keep that in mind. See if there was anything else that I meant to tell you. Okay. Now this function is always increasing, it's never going to change, right? And this is called a growth. When we talk about exponential functions, we have two categories, and this is called a growth. Hopefully that makes sense to you. It's used to model populations. It's used to model interest, which we'll talk about more tomorrow. This is actually pretty important in medical fields with like bacterial growth. If you have a bacteria that doubles every hour, that would be 2 to the x, and so its growth is modeled by this function. Okay, so this is a growth function. Questions on that? Okay, so make sure you let me know if you do have questions. Okay. So now let's do the same thing, but let's investigate what's going to happen when b is between 0 and 1. Okay, so again, we don't want b to be negative, but we do want to look at those numbers about what happens when b is between 0 and 1. Okay, so think to yourself, make a prediction. Okay, I will remind you that a number that's between 0 and 1 is like a half. So ask yourself what happens when you multiply a number that's smaller than 1. Okay, do we get smaller? Do we get bigger? Okay, so come up with a hypothesis, and let's go over to Desmos again. And so again, here's what it looked like when it was 2 to the x-ish. Okay, now what's going to happen when I go between 0 and 1? So here we're at 1 at a flat line. Okay. And then once you get past 1, headed towards 0, we now have a function that is decreasing, right? It's going from high to low. So it's actually a flip over the y-axis. Okay. And so notice, okay, that we have a curve going downwards. Okay. So do we still have important points on our function? And the answer is yes. Let me get to a half maybe. Okay. So we did do a t-table for a half, so you could go look at these points. Okay. We'd still have 0, 1. I didn't show it to you, but yes, 0, 1, because a half to the 0 power is still 1. We also have at 1, we should have the base, which is 1/2. Okay. And if you could get it to hit it exactly, we would see that. Okay. Notice we still have an asymptote, but this time it's the positive x-axis. Okay. And this is no longer called a growth. Okay, so think to yourself what it might be called instead. Okay. So let's go ahead and look at what this looks like. So we're going to do something like that. It's not perfect. Okay. So we still have important points. And those important points are still the same. We have 0, 1, and 1b. Okay. What would you say your domain is on this graph? Okay. Well, yes, we still have no restrictions on x, so it's negative infinity to infinity. Okay. Your range, it still has to be above the x-axis. So we have 0 to infinity. Okay, we still have a horizontal asymptote, but this time it is the positive x-axis. That's the line that it's approaching closer and closer to. Okay. This is called a decay. So we have growths, we have decays. Decays model like depreciation. It models also carbon decay, like carbon-14 dating and things. They use that. So half-lives. So those are some scientific applications that we will get into hopefully in the future. I meant to write this up there, but this is a decreasing function. Left to right, it's getting smaller. Okay. Up above, it was an increasing function. I mentioned it, but I forgot to write it down. So which one would e to the x be? Okay, well, it's a growth because b is equal to 2.7, which is greater than 1. Okay, so what about 2 to the x? Is that a growth or a decay? Okay, should also be a growth. Okay. But 3/5 to the x is going to be a decay because it's between 0 and 1. So here a growth, we would know that 2 to the x looks like that. We would know that 3/5 to the x would look like that. Okay. So now I would like us to look at some transformations, and I would just expect you to be able to describe them as well as match them to a graph. Okay, that's what you'll be doing on IXL, is matching to a graph. Okay, so let's look at our transformations. And if you have that cheat sheet we made before, that would be helpful. If not, I will see if I can scan one in for you, if I can find it. Okay. Or maybe you can talk to a friend and see if they have one. Okay. So let's say we have f of x, which is 3 to the x. Okay, what are some things you could tell me about it? Okay. Well, hopefully you could tell me that it's a growth, okay, because 3 is bigger than 1. Okay, give me just a second and I will be right back. Sorry, I can't pause on this. So we know that it's a growth. It's at 3 to the x. Just a quick note, we know that this is 0, 1. We also know we'd have a point at 1, 3. Okay, so those are some things that I would expect you to know, okay, looking at 3 to the x. Now the question is, okay, what happens when I have this negative 4 up there? What's that do to our graph? Okay, well, my first question, is it with x or not with x? Okay, so it is with x. Okay, so that means it's a horizontal translation. Okay, because remember x controls left and right. And when it's a negative, it moves opposite of what we think when it's with x. And so this is actually a horizontal translation of 3 to the x, and we're going to move it right 3. Okay, so that's what I would expect you to do. Okay. Did this change our domain any? Okay. Well, since our domain is negative infinity to infinity, adding 3 or subtracting 3 in this case does not change it. Okay. Range, did it change any? No, because we didn't move it up or down, so it would still be 0 to infinity. Okay. So let's go check real quick and make sure that our suppositions are right. So let's say 3 to the x is my first one, and 3 to the, whoops, get rid of the slider there. Okay. Y equals 3 to the x minus 2. And that's not right because the minus 2 is in the wrong place. Okay. Guess we'll put a parenthesis around there. Okay. So here you can see that red was my original and green is my new one, and it took this point here, 0, 1, and it moved it over 2. Okay, and it took this point over and moved it 2. So I do feel comfortable that we are correct in saying that we moved right 2. Okay, so let's look at another one. How about if we have f of x equals 4 to the x and g of x equals 4 to the x plus 1. Okay. So again, what I would expect you to know is that 4 to the x is a growth. And we would have a point at 1, 4, and we'd have a point at 0, 1. Those are good starters. Okay. Now, what's changed between the 4 to the x? Okay. Well, we've added this 1 here. So my question is it with x? And the answer is no. Okay. It's at a different level than x. Okay. So that means it's vertical translation. And what happens when we add a number? Okay, that's when we move it up. Okay, so it's a vertical translation of up 1. So that moves everything up. So let's look at our domain. Did we mess with our x any? No, so it should be negative infinity to infinity. Range, did we move it up or down? Yes. Okay. And originally our range, is 0 to infinity, and we've moved it up 1. So we need to add 1 to everything. So 0 now becomes 1, and an infinity plus 1 is still just infinity. Okay, so it just goes from 1 to infinity. Okay, so let's look at Desmos again. And we'll put 4 to the x in there. And we'll have 4 to the x. But we'll add 1. And so now you'll notice that the green did move up 1. 0, 1 became 0, 2. Okay, and so this is a vertical translation of up 1. How about we have 10 to the x, and we have g to the x equals 10 to the negative x, okay, plus 3. So this would be what happens when we have a negative with the x? Negative times. Okay, this is a reflection And when it's with the x, it's over the, which axis? So it's a reflection over the y-axis. Okay. And then this plus 3 is a horizontal translation. And it should move it. Let's see. I should have thought about this. If we pulled out the negative, this will be x minus 3. So I'm going to say it moves it right 3, but I may have to back off that one. I should have looked at that one previously. Sorry. Okay, so let's go see what we have. Oops, I forgot to take you with me. So let's go over there. So 10 to the x should still have a growth. So we have 10 to the negative x. Okay, so it flips it over the y-axis, and then if we put 3, got to put it up there with it, which means I've got to put parentheses, sorry. Okay, so it moved it right 3. And I know this one's strange. It's because of the negative. Okay, we had to pull out that negative, so I'll try not to give you anything like that, but I did want you to see that. Okay, so looking at our domain, what would you say we have? Still negative infinity to infinity, and our range is still 0 to infinity. We did not move it up or down any. Okay, so let's go back and let's see. Let's take 0.3 to the x. Actually, we'll try 0.2 to the x. Okay, so if we have 0.2 to the x, and then g of x equals negative 0.2 to the x, okay, plus 5. So think about what you think it might happen, and let's go ahead and graph it and see. I do think you should be able to do these without graphing, but if you need graphing to help, that's always a good thing to do. Okay. Hopefully you're not surprised to see it do the, forgot to take you with me to Desmos again. Hopefully you're not surprised to see it be a decay, because we did talk about it as less than 1. Okay. Now we do have a negative on this outside. So that flips it over the x-axis. That's what that negative without the x does. Okay, and then adding 5 to it should move it up. Okay. So we made it go upside down, and then it moved up 5. Okay, because of the plus 5 that is not with x. Okay, so let's